Hi everyone, let's look at handout 8.3, evaluating logarithms. So if you remember from last time, we had defined a logarithm in two ways. The first way is as an inverse of y equals b to the x. In other words, the exponential form of a logarithm is x equals b to the y. We're taking an inverse here, and we said that this is a log in exponential form. And then we said that there's a definition from this of a logarithm in logarithmic form. Okay, and that is basically, it's not basically, it is equal to the same thing. But we write it as y equals log base b of x. And essentially, these are both saying the same thing. What exponent do you raise b to in order to get x? So the answer is an exponent. Okay, so what we're going to do is review some log laws. And these are things that come from exponent laws. So I'm going to show you how to evaluate these without using a calculator, and then we're going to talk about how to use your calculator to do this. So if I look at the first one, log base 4 of 64, what I can do to solve this is actually set it equal to a and then rearrange it. So right now it's in the form of y equals log bx, and what I want to do is rearrange it into x equals b to the y. So I know my base is 4 to the power of, in this case, a equals 64, and then I can solve by inspection. So I know that 64 can be written as 4 to the 3, I believe, and therefore, if left-hand side equals right-hand side, I know that a must be equal to 3. So one way to solve is by writing a log in exponential form and then knowing what we know about exponentials to solve it. Okay, let's do it again. So if I have log base 3 of 1 over 27 and I let that equal a, what I can do now is rewrite this as 3 to the power of a equals 1 over 27. Then I have to remember how to write 27 as a power of with base 3. Okay, and you can trust me in that it is 3 to the exponent negative 3. Therefore, a is negative 3. Now, if I put this in my calculator, I would get the same thing. All right, a couple more times. If I let this equal a, 2 to the power of a is negative 4. And then we should recognize that this is impossible because the power on the left-hand side is positive, the power on the right-hand side is negative, and you cannot obtain negative 4 from a power of base 2. So no a satisfies this equation. Therefore, we can just say D and E does not exist. Okay, now let's look at a radical. So again, I'm going to set this equal to a, and what this is saying is 5 to the power of a equals, hopefully, actually, we can write it one more time, like this. Okay, and if you recall, I believe it's a m over n equals a to the m square root n. This is a rule you would have learned last year. Okay, so we can actually rewrite this radical as a power. It's 1/5. Okay, and now what we can do is we can rewrite 25, because I know 25 is 5 root 2. We call this a change of base. So I'm changing the base of 25 to a base of 5. So instead of 25, I'm writing 5 squared. Okay, and then if you also remember this rule, okay, if I want to simplify the right-hand side, I get 5 to the power of a equals 5, and 2 times 1/5 is 2/5. So we have a is 2/5. Okay, so we don't need a calculator for these ones, just we need to remember some exponent rules, and we need to understand the definition of a log in log form, a log in exponential form. Okay, so we want to determine the approximate value, okay, of log base 5 of 47. So if I kind of go down the same road, okay, what I'm saying here is 5 to the power of a equals 47. Now, I know this is not true, but I can make an estimate. I know that 5 squared is 25. I know that 5 cubed is 125. If I want to estimate it, I can just kind of throw it in my calculator. So I can start by doing something like 5 to the power of 2.1, because I know it's going to land somewhere between 2 and 3, but closer to 2. I will get 29.37, 5 to the 2.2, etc. And what I'll land on eventually, if I do this long enough, is a to the 2.3922. Okay, so how did I get that? Well, it's kind of because I already know the answer, but you would eventually get there if you did this long enough. Thankfully, we don't have to do that. We can use our calculator in a minute, but right now, I want us to do it a different way. I want us to change the expression to the related exponential form, i.e. the inverse, and then use graphing technology. So we're still going to start with 5 to the power of a equals 47. But what I want to do is graph what we're calling the related exponential. So I want us to graph y equals 5 to the exponent x. And then I want to set that equal to y equals 47. And I want to see where they intersect. Okay, so I have already put this in. I meant to change that. So we've got y to the 47. Let's draw it in. All right, so when I actually, might look a little bit weird. I don't know if it's gonna let me do this. All right, here we go. So this is the graph of y equals 5 to the x. And if I look at where it intersects, hang on. Okay, we get 2.3922, 47. So indeed, we got it right. Let me take a photo of this. Okay, there we go. Okay, so now let's move on to stuff you would more do on a test. Okay, so what we're exploring right now are some common rules of logarithms that we can recycle and reuse when we are evaluating logarithms in the future. So I'm seeing log base 6 of 1. So if I let this equal a, okay, and I rewrite this, I get 6 to the power of a equals 1. To solve this, we can remember that 1 is anything to the power of 0. So if I rewrite this as 6 to the power of 0, I get left-hand side equals right-hand side by knowing that a equals 0. But further to this, if I had, a equals log of any base b of 1, this would simplify to b to the power of a equals 1, b to the power of a equals b to the 0, and a equals 0. So regardless of base, this is always true. Essentially, log any base of 1 equals 0. So I'm going to write that a little more officially. Okay. So this is true of any base, and of course we know that bases are never zero, okay? So this is rule number 1. We're gonna keep going with many similar things. So if I let log base 5 of 5 to the power of x equal a, I can rearrange this, and it looks a little bit funny, but if we take the same steps as we did before, it's this base to this exponent equals 5 to the exponent x, and right away we get that a equals x. So essentially, if I have any scenario, I'm just going to use a different letter here. I'm going to say, let's say k equals log base b of b to the, I'm just going to use another letter because I think we're recycling a little bit too much here. Okay, so my base and the base of my logarithm and the base of the power are the same. When I rewrite this, I'm going to get b to the exponent k equals b to the exponent m, k equals m. Okay, so what shakes out here is this rule that log base b of b to the m equals m. All right, next one. To explain rule number 3, it might be best to start with another example. So as a reminder, what we have been saying is if I have, I'm going to take this and rewrite it in a simplified way. So let's say we have 6 to the exponent, let's say p. So if I want to, now this is the only one on this page that is an exponential. So if I wanted to do something with an exponential, I could still do the same thing, meaning I could let it equal a. So 6 to the power of p is a. Now this is a logarithm in exponential form. So one thing I can do is take this and write it in log form. Okay, so what I'm going to do is take this and write it in log form. So that would give me p equals log base 6 of a. So let's imagine we're doing the same thing here. So I take 6 to the power of log base 6x, and I set that equal to a. What I'm going to do is rewrite this log that is currently in exponential form into log form. So I'm going to say that log base 6 of x equals log base 6 of a. And in order for these two things to be equal, it's clear to me that x has to equal a. Okay, so this derivation is a little bit different, but what follows from this is if I have a base b raised to log of the same base, also b, of x, that just reduces to x. All right, so you can see that these two are kind of similar, okay, where both of the bases are the same. I take log base b of b, or I take the exponent b to the exponent of log b. All right, let's keep going. Hi everyone. Okay, sorry, I keep getting interrupted. For this final rule, I'm actually just going to write the rule down instead of deriving it because we need a fact that we're not going to learn until later. And also, for most of you, your calculator will allow you to change a base. So let's say I have log base b of a, and for whatever reason, I want to change the base from b to another base. Let's call it c. So if I have log base b of a, what I can do is take log base c of a and divide it by log base c of b, and I end up getting the same thing. So if I look at this question for a second, if I want to change this base to base 10, let's say, I can do log base 10 of 3 divided by log base 10 of 2. This used to be a lot more handy when your calculator only had log and ln on it and didn't allow you to automatically just like enter in your base, but most calculators do that now. So this rule is a little bit, I don't want to say useless, but you guys don't need it for your calculators much anymore. Okay, let's put this into practice. So I want you to use your log key on your calculator. Okay, so we have 3 options. Ln is log base e. So it's just short form for log of e, where it is the inverse function of e to the x. Log, when it has nothing there, there's a invisible 10 there, so that's just log base 10. And log base b is when b can be anything. Okay, so I want you to take a second and look at these, and you can use your calculator to check, but basically I want you to know that in order to do this, you can just use what you know about exponents, because log is just log base 10. Log base 10 of 1000 can be written as log base 10 of 10 to the power of 3, and we know using rule, what did I call that? Using rule 2, okay, that this just reduces to 3. Same deal here, log base 10, 10 to the 1. This is just 1. Log base 10 of, okay, so how do we do this one when this is equal to 1? Actually, did we do this? Yes. So I can just use rule number 1. This is 0. Log base 10 of, and we know this is the same as 1/10, log base 10, which is 10 to the negative 1. So using rule 2, okay, we know that this is negative 1. Okay, so we're going to evaluate log base 5 of 45 in 2 ways. So what I can do is if I want to use the log base 10, and I'm actually going to get rid of it. So now we know that log equals log base 10. I'm just going to say log 47 over log 5. Okay, and that's rule number 4. And I do believe that this is 2.3922. Okay, or we can just slap it in our calculator directly and do log base 5 of 45. So I want you to try that. You're going to have log base b, and you have to put in b as 5. Okay, give that a try. You'll get the same answer. This is the same question we did earlier. Okay, guys, I want you to try this next one on your own. Okay, and I will post the answer for you to look at. So check out my iPad notes online. Okay, so I want you to work on this now. Give it a check. It's already there. Thanks, guys. Bye.